Okay, so these are the kinds of questions we're gonna be able to answer at the end of this class. We're not going to do this one right now, but because it's just an example. Father's 4 times as old as his daughter. In 6 years, he'll be 3 times as old as his daughter, as she will be. How old is the daughter now? So, in order to answer these kinds of questions, there are really common models that we're going to use frequently. The most common ones are rate times time equals distance, and whole times percent equals part. So these are the most common setups for these story problems. So a few general guidelines when you're working with story opportunities. Don't rush to write down an equation. Okay, so it is not normal for someone to be able to read a word problem and write down the equation that needs to be solved. Okay, even great mathematicians can't do that. They do some work to figure out the equation first. So spend some time to understand the problem. Try to identify the relevant pieces of information. You might underline things, figure out how the different pieces relate to each other, draw a picture or make a table to organize your information. Then look for a model, whether you have or can use a common one. Like if they're giving you stuff about speed and time and asking you a question about distance, you would say, oh, I'm going to use the RT equals D model. Or they might give you one in the problem. And then once you have set up an equation, you can use some numbers to test that it's the correct one. So we're going to work through 3 of them together, and then you're going to do a few on your own for practice while I'm here. Okay, so a mixture problem. This is a really classic college algebra word problem. We have 300 milliliters of a solution that is 60% acid, and we want to make a solution that's 50% acid, but we only have jugs that are labeled 60% and 30%, right? But we want 50%. Okay, so we have 300 milliliters at 60%. How much 30% should we add to it? Because 30% will dilute it. How much 30% should we add to it so that we end up with a 50% solution? So the first thing is define your variables. So the way I always define my variables is to locate the question and let X be the answer to the question. Okay, so they said, how much of a 30% solution should we add? So we're going to let X be the amount of 30% solution added. So you identify the question and let the answer to that question be your variable. Then when you're done solving your equation and you end up with X equals, that's the answer to your question. Okay, so then we're going to draw a diagram just to wrap our brains around what they're asking us. So we have 300 milliliters of a 60% acid. So draw a little beaker here and fill it to 300 milliliters and label it 60% acid. Okay. And then I have to add to this some unknown amount of 30% acid. Okay, so I'm going to pour in from a, oops, looks like a coat hanger. It's supposed to be one of an Erlenmeyer flask, right? Okay, I'm going to pour some liquid in here, and this guy is labeled 30%. And how much am I pouring in? X, yeah, we don't know. We decided to call that amount X milliliters. And then after we pour it in, right, my, what? The composition of the two, yep. The beaker, right, is now going to be labeled 50%. And how many milliliters is it full to? plus x. We had 300 to begin with. I'm pouring x more in, so it's going to be filled up to 300 plus x milliliters. So once you draw the picture, there's a much clearer idea of what's happening and where the variables are and how they're interacting. So now we have the picture. You don't always have to draw a picture, but it's always a good place to start. If you're like, I just don't know what to do, draw a picture. Even if you don't see how it's going to help you, it can often spark an idea of how to write an equation. So once you have your diagram, organize our ideas and work into a table. Okay. So I'm using a common model because there are percents in this question. I'm going to use whole times percent equals part. So this is whole percent part. And in this case, the whole is the amount of solution, and the part is the amount of pure acid in the solution. Because a solution is made up of some acid and some water. So my 60% solution, how much of it do I have? 300 milliliters. I'll put 300 in here. And what is its percent acid? 60. I'm going to do that as a decimal, 0.6. And then whole times percent equals part. So if I take 60% of 300, that will give me pure acid if I were to say evaporate out all the water, right? So how much pure acid is in that solution? 180 milliliters. 0.6 times 300. Okay, now my 30% solution, how much of it am I pouring in? X. And it is 30%, so I'm going to put a 0.3 here. And then whole times percent equals part. So here I would have 0.3x. My resulting solution after I've mixed the two, how much total liquid is going to be in there? 300 plus x, yeah. 300 milliliters plus the x milliliters I poured in. It's going to be 50% solution. Now I just have one box to fill in. One box of information to fill in. And I have two ways to calculate that last box. I could either do whole times percent equals part, and that will give me the total amount of acid in my solution, of pure acid. So I could do 0.5 times 300 plus x. Okay. That tells me how much pure acid is in my mixture. Or if I want to know how much pure acid is in my mixture, I take the amount of pure acid that I started with and add to it the amount of pure acid that came from the solution I added. So if I add these two, I will get the pure acid in the resulting solution. So this should equal 180 plus 0.3x. So there's two ways to calculate that final box, so they have to be the same value. So we make them equal, and then we can just solve this linear equation. So we have 150 plus 0.5x equals 180 plus 0.3x. Subtract 0.3x from both sides. Subtract 150 from both sides. Divide both sides by 0.2. So we get x equals 150. I think it's 150. Let me double check myself here. 30 divided by 0.2, 150. So that's our question. That's the answer to our question, x. we should add 150 milliliters of the 30% solution. So what do you think? You could do it on your own? I'll take no response as we should do some more together. Okay, so now we have another example. This is still a mixture problem. It's just that this time we're mixing two kinds of investments. Okay. So we have a scholarship fund that has $10,000 in it. We can invest in two funds. One's low risk, one's high risk. From the low risk fund, we expect a return of 4% annually, and from the high risk fund, we expect to get 8% annually. We want to have an expected return of $550 a year, and we want to put as little money in the high risk fund as possible. So how much should we invest in each fund? So first, define our variables by locating the question and letting your variables answer it. Okay, so how much should we invest in each fund? So we're going to let X be the amount invested, and you could either do the high risk or the low risk, it doesn't matter. Invested in, let's say, the high risk. So if we're going to invest X dollars in the high risk fund, how many dollars are we going to invest in the low risk fund? Y, or 10,000 minus X. You could do, because it's a total of $10,000. So let's call it Y, because then this will give us some experience using two variables. Y will be the amount invested in the low risk fund. So then we fill in our table. So this is still whole times percent equals part. Okay, so the whole is the whole amount we invest. The interest is our percentage, and the part is the interest that we earn. So in the lower rate, the lower rate is the lower risk, right? So this is Y. And then the amount I'm investing in the higher risk, higher rate fund, that's X. And in total, how much am I investing? X plus Y, but I also know that X plus Y is $10,000. I'm investing $10,000 total. And then my percent interest, my lower rate was getting 4%, so we'll do 0.04. Higher rate is 8%. They didn't tell me what my percentage is going to be on my mixture of the two investments, so we'll just leave it blank for now. Fill in the things that they told me directly. So the amount of interest I'm going to earn, whole times percent equals part, right? So I'm going to earn 4% of Y and 8% of X. And how much interest am I going to earn on my total? What do I want to earn? $550. So I could figure out a percentage here. I could figure out what percentage is 550 of 10,000. So I do 550 divided by 10,000, and I get 0.055, 5.5%. I want to get a 5.5% return on my $10,000 investment. I might not even need to know that. Nope, we absolutely don't. But some people like to fill in the boxes. Okay, so I have two unknowns here, X and Y, which means I need two equations. You gave me one already. When I was doing this column, we said X plus Y has to add up to 10,000. The amount we put in the low risk plus the amount we put in the high risk has to add up to $10,000. All right, now my other equation is that the amount of money I make from my low risk plus the amount of money I make from my high risk has to add up to $550. My interest earned from the low rate plus the interest I earn from the high rate is supposed to give me $550. So I have 0.04 y plus 0.08 x has to equal 550. So when you have two equations and two unknowns, how do you solve? Anybody remember? Yeah. Yeah. Great. Great. So let's solve for y. Y is 10,000 minus x. So then in the other equation, you replace the y with the 10,000 minus x. So I have 0.04 times 10,000 minus x plus 0.08x equals 550. And now I only have one unknown in the second equation. So I can solve for x. So 0.04 times 10,000, 400. So 400 minus 0.04x plus 0.08x equals 550. Combine the like terms there, and I have 400 plus 0.08x equals 550. Subtract 400 from both sides. And divide both sides by 0.08. Yes, thank you. Yeah, because negative 0.04 plus 0.08 should give me positive 0.04. And I think I said it and wrote something different. Okay, so 150 divided by 0.04 is 3,750. So that's the amount of money that should be invested at the high risk rate. Okay. And then y, the amount of money I put in low risk, is going to be 10,000 minus that. 10,000 minus 3,750. 6,250. So this is low risk, high risk. So very similar to the last one in terms of the structure, that we used the same model, whole times percent equals part. This time we're just mixing money instead of acid. Sure, yeah. Checking is always a good idea. So we have two amounts that we should invest. We should double check that they add up to 10,000. And then we should say, well, if I get 4% of this, so I'm going to take 4% of 6,250. I get $250, right? 4% of 6,250 is $250. And then I'm going to take 8% of my 3,750. 0.08 times 3,750, and I get $300. Oops. $300. And 250 plus 300 is the 550 that I was hoping for. Yes, you can always go back and check that you've satisfied what the question asked you for. All right, one more together. So two cyclists, they're 90 miles apart. They're going to be riding towards each other at the same time. One is going to go twice as fast as the other. And they're going to meet 2 hours later. And the question is, how fast were they traveling if they meet 2 hours, if it takes them 2 hours to meet? So this is clearly a rate, time, distance problem. They're asking about speed. They've given me distances and times. So I'm going to use the common model, rate times time equals distance. But before I start trying to plug into a table, I'm going to define my variable based on the question. What average speed is each cyclist traveling? So let's say the slower cyclist speed, the slower cyclist's speed, we can call x. Okay, which means what is the faster cyclist's speed? 2x, because one's going twice as fast as the other. Okay, so we have our variable expressions. Slower cyclist, x. Faster cyclist, 2x. And it's a little weird to think about what is the combined speed, because they're moving towards each other. So I'm just going to leave it and fill in as much as I can, and maybe I don't need it, and if I do, I'll figure it out then. Okay, so we fill in all the things that we definitely know for sure. So what do we know about time? 2 hours. They both travel for 2 hours. Okay. And then we know rate times time equals distance. So the slower cyclist travels 2x miles, because they're going miles per hour times 2 hours, they go 2x miles. And the faster cyclist goes twice as far, because she's going twice as fast. She travels 4x miles. Okay. And together, how much ground do they cover? 90 miles. So the whole trip is 90 miles. And if we add up how far the slower cyclist traveled with how far the faster cyclist traveled, they traveled together 90 miles. So we'll say 2x plus 4x is 90, and it turns out there's a couple boxes I didn't really need. So we get 6x is 90, which means x is 15. Okay, so my slower cyclist is traveling at 15 miles per hour, and the faster cyclist must have a motor, right? That's really fast. 30 miles per hour, or maybe she was going downhill or something. Oh, wow. So maybe it's a professional. All right, so really the only way to get good at these is not to watch me showing you how to do it, but to get your hands dirty and start doing some. So I have a worksheet, should be on the next page, or maybe the page after that. Modeling with linear equations. I want you to work through these problems in your groups. And I actually gave you a little helper chart on each of them for the worksheet. And your homework, you're going to have to make your own little chart. So this is like a stepping stone. And yes, you do have the answers, I believe. Yeah, the bottom of the second page.